अरे ती किरण आहे ना तिची मैत्रीण पण मेसेज केला मगाशी मला. नंतर कोणतरी कॉल करते तिला. हा सांगता संजना पाटील आहे आणि ट्रू कॉलर वरती बघितलं तर त्यांच्याच वर्गाचा तर मुलगा आहे कोण पंकज सुतार असं आहे काहीतरी आणि त्याला
Okay, so hello everyone. I hope all of you are doing great, and I welcome you to all the last episode of the FOSS Files series, that is the Quantum Quest. Since it's the last episode, I want all of you to spam in the chat box that hashtag the FOSS Files. So let us start with great enthusiasm. Okay, I see many of you commenting. So before starting, can we just recall? Can anyone tell what topics we covered in the last episode? What was the main topics that highlights that you remember from the last episode? What was your favorite topic from the last episode? Okay, crypto and public private keys. Cryptography, right. Also, we had known about blockchain, right? And we got to know one of the major application of blockchain, that is cryptocurrencies. Also, we got to know something more about PGP, GPG, etc. Right? And lastly, SSL. Can anyone tell me the full form of SSL? Okay, one comment is about secure socket layer. Others do response if it's right or wrong. I don't think so. The answer is right. What other things? Okay, so the answer is right. Secure socket layer. Uh, Also, in today's session, we will learn something about quantum cryptography. Has anyone heard about quantum cryptography before? Since our podcast name include the quantum quest, has anyone any idea about what is quantum cryptography? Am I audible? Okay, so no worries. We're gonna see about quantum cryptography in today's podcast. So comment ready. Let's go in the chat box so we can start off with the today's podcast. All of you are excited? Yeah, I can see in the chat box many of us are excited. So let us begin with today's podcast. One thing I see that I didn't get the answer of the secure socket layer. Is it right or wrong? I didn't get the. I said it was right, but what do you guys think? Let's see. Suppose if the answer, let's if the answer is right, can you explain a bit more about SSL? What did you learn from the past session? What is SSL?
Okay, hello. Is the screen visible? Hello, am I audible? Yes.
Yes,
Okay,
yes.
thank you, Rameshwari. That was a great getting to know everyone's session. And now uh, is I think we should start with our session, right? So the quantum quest. Okay. So in the last three episodes, we obviously saw the major things, the things which everyone uses everywhere. But today we'll explore some lesser known parts about cryptography, things like steganography, which are used actually, but they are not that visible to us, and also the future of cryptography. So I welcome our speakers, Ajinkya and Shreyas, and I'm Aditya Aparad. So let's start. Okay.
Okay, thank you Aditya for the introduction. So let us begin with our last episode. Today we are going to look into steganography, homographic encryption, Shamir secret sharing, and the topic everybody is excited for, post quantum cryptography. So before beginning steganography, I would for the previous episodes you guys learned about cryptography, right? Can someone tell me what cryptography achieves in simple terms? Like what is the main goal of cryptography? All the encryption and decryption you did. Okay, Aditya says protection of data, hiding of data. Okay, yes, all the things are right. It they protect the data. It helps cryptography helps hiding the data, and by hashes we can check the integrity. But for steganography, I am interested in the aspect of cryptography that, like for example, let us say you send a message to your friend, and in between some other third party intercepts your message. Now, because the message was encrypted, even if the third party obtains that message, they won't be able to know its meaning. Am I clear? That is what encryption does, right? On the other hand, steganography is hiding the fact that you sent a message at all. Okay, it might be confusing to hear. When in encryption, you send the message to some classical means like email, messaging through, let us say, some app, right? So the third party knows that you are going to send a message through these apps or these emails, so they can intercept. Steganography is like hiding through which you are going to send the message. So it is the practice of concealing information within another medium. Now, steganography is derived from two Greek words, that is stegenos, meaning covered, and graphy, meaning writing. So, the most basic type of steganography can be hiding data in images. So, that is one of the types. Image steganography means hiding data in images. Audio steganography means hiding data in audio files. And network steganography means it is hiding data in network protocols and related network equipments. So, uh, do you people know about that one pen you used to get at Zatras and Yatras? If you write with that pen, it was not visible with naked eye, but if you saw it under UV light, it was visible. Did anyone use such kind of pen? Yes, right. That is the most simplest type of steganography. Like you send a letter, written letter to your friend. You write one side with your normal ball pen, it will be visible to everyone else. And you write another side with that hidden ink. Even if you pass that letter through multiple friends till it reaches its destiny, the third party doesn't know that they will only read the message written by the ball pen and not by the invisible, because they don't know that you have to specifically look under a UV light, right? So that is steganography. It is hiding information under the nose of that third party. Everyone clear with the basic premise of steganography? Okay. So let's move forward. For this episode, we will focus on image steganography and one of its type. So these are two images many of you might recognize. This cat. Does anyone recognize this cat? Yes, it's the baguette cat. Now the question is not what cat it is. I'm just, can anyone tell me what is the difference between these two images? Can you visually discern between these two images? I want you to tell, I want you all guys to tell me what changes you notice. Visually, these two images. Okay. If you see correctly, visually, these two images are the same images. Like they are pretty imperceptible. But I am going to tell you a tool through which you can tell which one has the hidden message. So for this, we are going to look at the steganographic encoder and decoder. This is a free tool by a GitHub author known Styles. And the fun fact about this website is that he has managed to encode steganographic information through pure HTML and JavaScript only. Nothing else. So
Okay. If everyone has scanned it, uh, I have the images and I can show you the differences between them. Shall we? So, firstly, I have the two images. I'll switch to my terminal. Can everyone see my terminal? So, this is a simple tool, XF tool, through which I've run these two images. They both are named image1 and image2.png in these two tabs. Okay. So, if you can see, everything is same, and I'll switch between these two images, and you can see only the file name and the file modification date is different. Rest everything is the same. Can you see it? All all the data, the especially the image data, like image width, image height, bit depth, everything, and you can see the image size is exactly that. Also, the file size is exactly the same. Even if we encode any information, the file size didn't change at all.
So if you guess that you might store the data in metadata or some other field, it is not that, because now Aditya is showing us directly the metadata of that image. So both of them are same. So we are not hiding data in plain metadata. It would be too naive to hide actually. I would
So,
like to point, 1 minute, I would like to point the bit depth, that is 8. Guys, just remember that the bit depth is 8. Okay, continue.
all right. So now I'll go to that tool that Shreyas mentioned. What is this one? Steganography Online. So it has two tabs. One where you can choose your image file and then you can encode any message. So we have already done that, and one of those two images had some data. So I'll choose the first image, let's say. So I've chosen this image. Can everyone see this image? Yes. So I'll just press decode here. You can see there's a button. Because there is no encryption right now, you can see uh, you can directly get this message. This ginger is really cute. That was the message encoded in this image. Should we try the other one? I'll choose the image 2 now. Okay, and then I'll press decode. You can see there is no hidden message here. So there was hidden message in one but not in the other. We hid information in plain sight. That is the fundamental of steganography. Are we hiding it in .dat file? Which DAT file? There is only one file actually. The I think the format is PNG.
Yes, it is just a PNG image.
All these formats have support for metadata, but we are not hiding it in there actually. We are hiding it in the pixel information of the image. Great. So let us switch back to our presentation.
Now let me explain how the data was encoded. Now many of you guys guessed in .dat file or some metadata, but it is not that. It is actually a bit smart. So this type of steganography is least significant bit manipulation image steganography. In this, we change the least significant bit of each pixels to encode our data. Now can anyone tell me what are least significant bits? We can say that least significant, okay, whose contribution to binary is less, rightmost bits. Yes, least significant bits are basically the rightmost bits in our binary representation. So let us assume now all data of computer is stored as binary, right? Zeros or ones. So let us assume to our data to be 10, 01 and 11, like I have written here. And let us assume pixel information for the 3 pixels, these are sample, as the following. Now if you count this, these are 8 bits in length. I told you to remember 8 bit depth, 8, right? The reason for that is each pixel in the image uses 8 bits to store its color information. Now, generally, color information is stored as RGB, 3 primary colors, and its combinations make up all the others. So, these 8 bits define what combination of RGB the pixel has to show. So let us assume these 3 values for 3 sample pixels. So the data is given, then we change the pixels least significant bit to our data directly. We basically override the original information of the pixel it had, but we just change the least significant bit. Now you might say it changes the color. Well, it is right. The max change is 3 because in the last pixel we changed 00 to 11, right? So this change is just max of 3. So in the grand scheme of things, the color difference in these two is pretty imperceptible. So until and unless you don't have the original image to compare with, it is really hard to tell that this image was tampered with or it had its pixel information changed. So as we said, there is no change in metadata or size of the pixel, size of the image, sorry, because we are storing the information directly in the pixel itself, not anywhere else. Is everyone clear with this smart implementation? Guys, any doubts? If you have any doubt, you're free to unmute your mic.
Is this interesting? Where do you think this can be applied?
Guys, please respond, then we'll move forward. If you didn't understand any of the things, please ask.
I have a doubt. There it is mentioned that for each pixel, the max value change is 3, right?
Yes.
So that uh, here the change is shown for 2 only. So like I can easily change the third last one also.
No. If you see, binary is calculated from left to right, right? The
Yeah.
right to left. So the rightmost has the value 1, then the one after it has 2, and then the one after it has 4. So if you were to change the third bit as well, the max value change would be 7 if you calculate.
Oh, okay. In that format, be like 2 raised to 0, 2 raised to 1, and 2 raised to
Yes,
2. Here.
And
those
the
are
higher
bits,
the
right?
difference, then the more perceptible the difference is.
So the name of this technique is least significant bit manipulation because we are trying to be as imperceptible as possible. So we just change the last two, not more than that. Clear?
Yes, Bhaiya, clear.
Okay. Any other doubts? Okay, so let's move forward. Now it is not that this LSB image steganography is really impenetrable. It has its problem. The first one being the data holding capacity of LSB is very low because as we are storing data in just 2 bits of every pixel, to store a large amount of text or any other data, you need a lot of pixels to store that value because you just changed the last two. If you change more, you will get more data holding capacity, but you will ruin the image in that process. So that just defeats the purpose of steganography, right? Also, LSB is sensitive to image compression techniques. What do I mean by that? The image we used for our demonstration was .png. Do you guys know any other image format? JPJ, yes, that's one. It is one of the most widely used. .jpeg. Yes, these are the most used. Now, if we convert the original PNG to any of these, the data gets lost in the process. There is no way to hold that data because each image compression has its own technique, and interchanging that will messes with the LSB. And also cropping, rotating, or basically editing the image even in the smallest bit can destroy the data because it can mess with the sequencing or with the specific bits, so that even if we try to decode it, it just gets messed up. But there are more better alternatives to LSP like DCT, which is discrete cosine transform, and we also have masking and filtering techniques. Now you can check these techniques on your own because the implementation is pretty detailed, but these are pretty interesting to learn about. Where they are used? Well, do you guys know about DRM protected content online? Well, I'm pretty sure that you guys know about copyright protection or the ownership. DCT and masking and filtering are basically used to copyright some image so that illegal use can in masking and filtering especially we hide the data in less significant areas like edges or textures, and in such a way that even if the file compression or the edits are done, the data doesn't get we do not lose the data. You can search about this on your in your free time. These are really interesting. Now,
So, as far as I understand it, you mean that suppose I have a Netflix subscription and I try to pirate it by recording a show or something. So, my metadata, like my account information, will be secretly encoded by Netflix in that film itself. And then if I try to share it with someone, then they can obviously detect that I shared it first, and then they
yes,
will ban my account or something.
yes. You must have also
Okay.
like it is pretty vague example, but on our question papers, there you can see some numbers written in cross, some string written. Has anyone noticed? Yes, diagonally a string is written, new alphanumeric string. This is also a kind of masking and filtering. So if you are the one to click images and leak the paper, from that number they can track you back. This is kind of yes, even in 11th and 12th there are patterns. Those patterns are just copyright, and masking and filtering are basically copyright for image steganography. So even through editing or changing the compression, they still retain their information. Yes, also in currency notes. Yes. Okay, so is everyone clear? Okay, we'll move forward. Back to you, Ajinkya.
So now at all, we have learned very much about steganography. Okay, and it is kind of interesting also. Similarly, now we are going to learn about a new kind of encryption technique that is nothing but homomorphic encryption. Now, seeing on slide, you can see it is kind of two words like homo and morphic. Can anyone in chat section tell me what does homo and what does morphic means? In simple terms. Of same kind. Okay. And what does morphic means? Right, Ashutosh. Homo means of same kind. Morphic means make or create. Okay. Any other responses? Type. Absolutely right. Or a form. So homomorphic is nothing but similar kind of forms. This encryption technique is based on this principle. Okay. So let's first see the definition. So it is a type of encryption that allows computations on encrypted data without actually decrypting it. So many times we have to perform some operations or computations on our data. Okay, so we have to give that data to a third party person or server or cloud, and he performs that computations. Okay, so in this encryption technique, instead of giving our regular data, what we will be giving the encrypted data of that. Okay, and he will perform operations on that encrypted data. All right, and the result when decrypted matches the result of operations performed on the original unencrypted data. So that is it. Means now operations are performed on that encrypted data. So now that server will return us that encrypted result of that data. So now I had given him that thing. So I will decrypt my result and will achieve the result that I want. So in this case, we have not given actually our regular data to that person. So this is the encryption technique which is based on this principle. So we can see here
Ajit, I
Yes.
think you
Now
are.
let's share some.
Okay, okay. Okay, continue.
Okay. So let's say he shared some valuable items like gold, platinum, diamond. He had kept in box like locked box and magical box. Now he had given me task to count how many gold items are there. Okay. So in locked box in general encryption, what I will do, I will simply count how many gold items are there. I will access them and will return a yes as the count of that gold items. Okay. But in magical box, which is this homomorphic encryption, what I will do, first of all, which will give me in encrypted format. Like these items present in magical box are not being accessed by me actually. Like I don't know this is gold, I don't know this is platinum. Okay, these are all in form of encrypted. Okay, so I will perform operations, will count, let's say X is that gold. Okay, now I will count the value of X and will give it to yes. So the same thing, that is operation is performed but in different way. So that's why homomorphic encryption. Now most of things must be cleared. Instead, let's take an example. Okay, so let's say I am that client. Now I have the data as 5 and 3, and my aim is to perform a addition of these data. Means I have to perform a 5 plus 3. So what I will do, first of all, I will encrypt 5 and 3. So after performing encryption, it will be like at the rate hash for 5, and it will be like ampersand star and exclamation for 3. Now this data I will provide to that third party person from which I want to perform addition. Okay. Now that third party person will perform addition on these encrypted data. Alright. Let's say he has performed the operation of addition, and the result of that addition will be this, like our factor percentage and dollar sign. Now this value will be returned by him to me. Okay. Now when I will get that value, I will decrypt it and I will get the result as 8. Now you can see here, instead of 5 plus 3, which is not known to that person, he had performed that operation and gave us the correct result, that is 8. So this is the beauty of this encryption. Alright. Now the types. Now based on their use cases, their criteria has been defined. So there are 3 types of homomorphic encryption. So you can see first is fully homomorphic encryption, that is FHE. Second, partially homomorphic encryption, and third, somewhat homomorphic encryption. So in FHE, now general computations are addition and multiplications. All right. So in FHE, you can perform these both operations at a time. Means addition and multiplication both can be performed. And you can perform these operations any number of times. Means you can perform this in infinite also. Now in PHE, that is partially homomorphic encryption, only one computation can be performed at a time. Means either addition or either multiplication. But thing is, you can perform that operation any number of times. And in SHE, both the operations can be performed. Means addition and multiplication both can be performed at a time. But case is, here we can perform that operations up to ample number of times only. That is, use case is limited here. Alright. So these are the various types of homomorphic encryption. Depending on the circumstances, any of that type can be used. Now you may be thinking like that. Now till episode 4, we have learned various encryption techniques. So how this defines differently through them? Means why can it be used? So first is nothing but it protects privacy during processing. So can anyone tell me what does privacy means? Means in simple terms, you can answer. If someone is typing. Sensitive data is protected. Absolutely correct. Any other responses? Ensuring confidentiality and authorization access, securing the personal data of individual. Absolutely correct. So let's say we take the example of hospital. All right, and there is doctor, and he want to count total number of people having the disease as diabetes in, let's say, any region. Now what he will do, he will give that data to a third party person like services like cloud services or remote services. Now he is going to give his actual data. So in that case, the privacy can be hindered. But do you think in homomorphic encryption, what we actually give is the encrypted format of our input data. So that third party person don't know actually what is the name of particular patient, what the age of that particular patient, and its diagnosis history. So it will be going to protect the privacy of that patients during the processing. Like here, the counting was the process. Okay. Now, second benefit is nothing but securing the data in the cloud. Now, what does cloud means? You can give your answer in simple terms only, but try to be interactive. Cloud. Virtual storage. Okay. Any other responses? Computers on rent. Okay. Absolutely nice. So what thing is securing the data in the cloud? Many times we have to perform some operations or computations on our data. So what we do, we give that data to particular remote services like cloud. Okay, that is virtual storage. So what that services do, they perform our operations and give us our result. Or any times we can store our data at that place also. So now here that data can be sensitive. Like you take the example of e-governance. All right, means the counting of voting. Now people cast their votes. So this is kind of sensitive information. Like someone has casted to a particular person, someone has to a particular person. So this is kind of sensitive information. So it must be securely stored. So in that case, that security storage of data or to perform operations on it can be done via this encryption technique. Now next is eliminating the trade-offs between security and functionality. So what does trade-off means? Like reading the sentence also, what does trade-offs means? Okay, yes, and they are typing. Guys, be interactive because if you can think upon this, then it will be a easy thing for you. So compromising one for another, absolutely right. Any other responses? Exchange of some sorts, all right. So continuous. So now in industry, there are various aims of a particular application. So in that, security and functionality are one of the most important things. So do you think for achieving one thing, we have to compromise another things at a time? Means not all, but at some cases, for attaining particular thing, we have to compromise on different things. This happens generally in most cases. So similarly, like if security and functionality, both the things we have to achieve, then this encryption technique will be much useful in that case, because you can see security. Now by using this encryption technique, the security of data can be managed efficiently, and functionality like computations on that data can also be done in homomorphic encryption. So it will trade off that concept, like it will not be a compromising thing in industries to to a particular thing like security or functionality, because both can be achieved. Now reduces the risk of data breaches. Now, had anyone heard about data breach? If yes, then surely mention it in comment box. Data breach. Okay, Aditya has mentioned one of the key thing. This technology is being researched and used in ML and DL. You can provide encrypted data to a cloud model and receive an output without having to lose your privacy. This is what this technique is based on and can be useful. So I was waiting for data breach. Any response? Someone is typing. Let's wait. Leak of data to unauthorized sources. Absolutely correct. So what the case is, like in broader aspects, the risk of data breach is much higher. Okay, like you have heard some news in recent days also, like this data got leaked. So in that case, if the regular data like his name, his age, gender, which is stored in actually format, is got leaked, then it will create an impact for that application also, and will be a sensitive issue in society also, because it may be containing private information also. But as in homomorphic encryption, we are going to store it in encrypted format. So even if that data is lost or data has been breached, that risk of data breaching, means using it for some other intentions, can be reduced because it is in the encrypted format. Now another application is it revolutionizes the industry applications. Now our industry is based on various applications. Now this will be a revolutionizing concept if we use this encryption technique in that case, because both operations and security is both is enhanced in this case. So it will be a revolutionizing concept. And last is empowers the regulatory compliance. Now in this case, as we are going to trust that third party person for our data, so if I give him in encrypted format, so the trust between that person and that third party servers or services is increased automatically, because that client had to no worry about that data can be lost or that data can be breached. So these were the benefits of using homomorphic encryption. Now last is nothing but challenges. Now you may be thinking like, here there are various benefits of using this technique. So all people may be using this technique. So, but there is not case, because there are some challenges also. Like first is high computational overhead. Oh yes, these algorithms are not very efficient because they work on encrypted data, right, Aditya? So high computational overhead. So what does overhead means? Can anyone tell? Overhead. Just in simple terms, you can answer. So overhead is nothing but doing particular operations another times, means instead of doing it for a particular time, yes, unnecessary operations. You can say it as a overhead. So as we know, in this technique, we encrypt our data. So it may be a case when new data comes, then computational overhead increases at that time also, because as it is on encrypted format, so computational expenses also increases. Now I am going to ask, what was the first type we seen in encryption techniques, that is homomorphic encryption? Like there were three types. So what was the first type we discussed before? Yes, fully homomorphic. So yeah, these are the three types, and from that FHE. So we can say FHE is most efficient because both operations can be performed, but it is kind of computationally expensive. So that's why using it becomes overhead at a particular times. So due to high computational overhead, it is being avoided at many times because computation increases when data increases, and in industry these are not based on practical operations, like they are based on real-time applications. So in that case, overhead increases. Now large ciphertext size. So what does ciphertext means? Now it is our fourth episode, so it is kind of simple question. Ciphertext.
We have discussed this term in every single episode, I think.
Yes. Ciphertext.
Ajinkya, let's hurry up a little because already it's
Yeah.
1 hour has passed.
Yeah, sure. So as encrypted data. So as if encrypted data is larger, that is large ciphertext, so the computations becomes heavier and the expenses also rises. So in that case, we have to avoid using this technique. And last one is nothing but limited practicality and scalability. Now we have to become practical because data is not a small entity. It becomes increasingly additive in real-time applications. And in that case, it will not be a practical solution for that. And scalability. So when data is increases, then this encryption technique is not scalable as the computations are overheading. So these were the challenges in this technique. So now after this, Shreyash will be going to talk upon Shamir's secret tree. So hand over to Shreyash.
Okay, Ajinkya, thank you. So, what was the third topic?
Does
Guys,
this name ring any bell? Shamir, have you heard this name in previous episodes? See, this is from now, all the topics from now are a little bit mathematically intense, but also very interesting.
okay, so let's start a third topic, that is Shamir's secret sharing. Now, he solves one of the most creative, one of the most widely uh, experienced problems in a creative way. Let's suppose you have a company and you have a council of 10 members. So, as this is a council, you need the vote of majority to pass any decision, right? So, in 10, let's say the majority is 6. So, if you get 6 yes, you can pass that decision. So, now your company has a lot of data on users and how they behave. Very critical and secret stuff. So you do not want everyone to have access to the data. So what do? You encrypt that data with a password. Now, if we give each the password to each of the 10 council members, even if one like betrays your company and tries to sell the data, they will have the complete access to the data, right? It won't be good. And let's say if a law enforcement or for some reason you need to decrypt the data, then you need to have the vote of power from your council to do so. Not just because two of those board members came together, they want to decrypt the data for their own personal agenda. You do not want them to happen. So, do you guys can you guys advise a way how they can share that password without one individual having too much authority and also respecting the vote of power? This is you guys can visualize this problem, right? The council, vote of power. Guys, respond. Yes, just like veto in UN. So this problem of password sharing was solved by Shamir's secret sharing. So it breaks the password into keys among n number of individuals with same power to everyone. So not all the keys are of the same power. Not one is powerful than others or less powerful than one. So in our example, we had a member council of 10. So you need 6 people to come together to pass a decision. We can also call this a KN scheme, where n is the number of people the key is shared with, in our case that is 10, and k is the minimum number of people required to crack the password. So how did Shamir solve this problem? Well, he visualized that problem and he generated the shared key through a polynomial function. Now you guys know what a polynomial function is, right? It is just a function of x. So let me ask you a small question. How many number of points are required to define a straight line? Uniquely defined. Two points, right? You need two distinct points to uniquely define that one single straight line. And if you take any n number of points on that already defined straight line, you can use those points to recreate the straight line itself. And so for a quadratic, you actually need 3 points. For a cubic equation, you need 4 points to uniquely define that curve. So we can conclude that if the k is the minimum number of persons required, k minus 1 polynomial function is required, meaning the power of that polynomial function must be k minus 1. So in our case, 6 was the minimum number of persons required to come together, right? So you needed a x raised to 5 polynomial equation to effectively use Shamir's secret sharing. Now, how did he do this? Basically, the equation is the answer to cracking the password set. So, just as I said, you need 2 points to uniquely define a straight line. So, if I have a council of, let's say, 4 members, so I will give any 4 random points on that straight line to those members, and even if any two of them come together, they can deduce the equation of the original straight line, right? Isn't that logical? Similarly with quadratic. it requires 3 unique points. And if I have a council of 5 members, I can give any 5 random points on that curve, and even if 3 people of those 5 come together with their points, they can deduce the original equation and they crack the password, right? This is Shamir's secret sharing, and the points on that curve that is shared, it is known as key sharding. So Shamir basically visualized that problem geometrically, and he devised this equation, which are basic polynomials, to solve our problem.
This is
So
cool too, right? Uh, does anyone see the brilliance here? He just took a polynomial equation and then we know the number of points it requires to uniquely define it, and the polynomial equation itself is the key. So even if we have one less, for example, we define a line with 2 points. If we have 1 point, there are infinitely many lines. So it is very secure, right? Yes.
similarly, for quadratic or parabolic curve, you need 3 unique points, and through 2 points, infinite many curves pass through. So you basically require those minimum number of points even if one is missing to crack the original password. Even if one is missing, you cannot crack it. Is everyone clear with this Shamir's secret sharing? Okay, that's
The
great.
polynomial itself is represented by the coefficients, uniquely defined by the coefficients. So you just store the coefficients and you concatenate like ax square plus bx plus c. So your key will be something like ABC.
Yes, or even intercepts of x or y are used to be the password. It can vary in its implementation.
Great.
Okay, so everyone is clear, it seems. Back to you, Aditya.
Okay, great. So now the topic that is in the title, quantum cryptography, right? Before that, let us discuss a few words about the future of cryptography. Why are we even discussing about all of this? So does anyone recognize this diagram? I think people who are not uh, in third year, I think they will not be able to recognize this. So this is basically a diagram of computational complexity. Yes, computer algorithms. So if you don't know about this, no need to worry. This is just basically classification of algorithms based on their complexity. Um, and this is not okay. Let me define this very simply. So you can see this in this Venn diagram. There is a section called P here. One second, let me get the cursor. Okay, can everyone see my cursor now on the screen? Right. So uh, this is the section of P, which means polynomial. This means NP, non-deterministic polynomial. So what that means is, suppose there are various algorithms. Uh, so algorithms of complexities, right? What is the complexity of binary search? Everyone knows that, at least log n. So all these algorithms which have polynomial complexity, like they can be the complexity can be defined as polynomial. They are put into this category, which is P, and imagine that the rest of them are put somewhere over here, if you don't know about this. So there's also other things like we can verify the solution and everything. We'll not go into that. I'll tell you what exactly it is. NPR algorithms which have, for example, exponential time complexity. So we cannot easily we cannot easily compute these algorithms for larger input values. So, okay, so right now we use algorithms like RSA, which are based on problems like the integer factorization problem, as we discussed. So, why is it secure from brute force? Because the factorization algorithm is believed to be in this class NP. That is why it is very hard for larger numbers for us to apply that algorithm and factorize it efficiently. Other Every single cryptographic algorithm, like why can't you reverse hashing? Hashing is one thing is that you lose information, but let's say other algorithms like DSA, digital signature algorithm. So the problems that those are based on are also in NP. And we have talked about numbers, huge numbers like uh, 2 raised to 256, 2 raised to 1024. So these exponential numbers, which are exponentially higher than normal numbers. And that is why all these algorithms are secure on a classical computer. Now, obviously, I don't think we will ever be able to uh, crack these algorithms. So the cryptographic landscape is always evolving. So, uh, some algorithms that might be considered secure now might not be considered secure in the future. For example, SHA-250, SHA-1, everyone has heard of it, Git uses it and everything. That was considered secure in the previous decade. But now, if there was a team of Google researchers who basically found vulnerabilities in SHA-1, and now it is not considered secure, it is considered deprecated. Again, algorithms like DES not considered secure. Previously, they were the standard. So right now the standard is all these algorithms. But in the future, these standards might change again. So why is that? Because as uh, everyone reads the news, there are quantum computers on the horizon. So let us try to get a feel, I think. I don't know how this will go, but we'll talk about a little bit of quantum mechanics and quantum computing. And then I hope we'll understand, we'll get a feel for why they are faster. Just will not go into very detail of a lot of these algorithms because frankly, I'm also not an expert and uh, it is a very intense topic, we can say. I've spent many days studying about this. Great. So some lightweight quantum mechanics. So I think everyone here has attended physics classes and knows about this experiment, Young's double slit experiment, where we basically emit light which goes through two slits and then makes an interference pattern on the screen here. Why is that? Does anyone remember? Yes, in the first year, I think there is a subject of physics. There also they teach you all these things. So one, this is what we now know as the dual nature of light, right? Light can be defined as both a particle and a wave. So we don't define it as that. We say that light has dual nature. So light is neither a particle nor a wave. It is what is known in a state of superposition. So what is superposition? Particle and wave. So it is not and particle. Light is not particle and a wave. It is neither. You see, it is in a completely different a state which we call superposition. So why do we call this a superposition? Because light, as let's imagine this, a single particle of light, a single particle of light going through here. So because we know that light can also be defined as a, not defined again. Light also acts as a wave. Uh, the position of that particle, you can say, is not very well defined. It is spread throughout that wave. And this is what we call, the wave is what we call a set of states. So the light particle can be here. All these points that you see, that would be the position of that light particle. and that is what is known as the state of that light particle. And this all of these states can be individually represented by a wave, and then the superposition. So you have heard about this term, right? Superposition, this thing. So uh, all those positions, when we add up, we get a set of states which we now know is known as the Schrodinger's wave equation. Okay, so some superposition again. So we know that some quantum particles. Firstly, before we move into this, I will ask you to keep aside your intuition, because quantum mechanics does not uh, submit to our intuition, human intuition, but it works. This is basically pure mathematics and it works. That is why we use it. So there, what we find is that some objects, small objects, quantum objects, follow this principle of superposition where the state is not precisely defined. Like here, the position of that light particle was not precisely defined. It was defined anywhere in that wave, and eventually when it hits the screen, that is when it is uh, observed, we call it, it collapses into one point. We'll see why that happens. So on some other particles that exhibit this thing, the famous examples are electron spin. So electrons, as we know, can have a property known as spin, in which has two values, either spin up and spin down. So imagine you have an electron that you have not observed. That is, you don't know what its spin is. So its spin is not very well defined, as we call it. It is in a superposition of both up and down. So what is superposition? What does it mean for an electron to exist in a superposition? So suppose there is an electron with spin up and there is an electron with spin down. So these both have their own waves. And if we add up those waves, then we get the actual Schrodinger's equation of the electron in superposition. So another famous example is the polarization of light, where you know what polarization is, right? In the wave picture of light, the plane through which the electric and magnetic waves pass, that plane. So normally what light has is, it is unpolarized. What that means is, we don't precisely know its polarization. It is also in a superposition. And then when we actually measure something, we interact with it, then its polarization, it's fixed. So that is what is known as the wave function collapse also. All right. So this is the most famous thought experiment. I think everyone knows here. Schrodinger's cat thought experiment. Who has heard of this? Are these things getting clear? I know this is not intuitive, but just superposition is just a quantum object, which can have multiple states, and it is defined by those multiple states. There is no single state. Okay. Yes, dead or alive. So this is a thought experiment in which this guy Schrodinger did was, he took a box and then he put a cat inside it and then a radioactive atom. And if that atom decays, then this detector detects it and releases poison, and then this cat dies. So there, thing we know for sure is that radioactive atoms are in a quantum superposition also. So they are in a superposition of two states, that is either decayed or not decayed. And because they are in a superposition, there is another property of quantum mechanics that we know, which is known as entanglement. So what happens in entanglement is, because this has a wave equation called this has its own Schrodinger's wave equation. The detector has its own Schrodinger's wave equation, and the cat also has its own wave equation. So because these equations interact, they all become a single state. That is, they all exist in entanglement, we call it. And this box is hypothetical box that prevents any entanglement outside this box. So what happens is because this is in a superposition, all of these states are entangled, then we can say that this cat is both dead and alive at the same time, because it is in a that is a very weird way to define it. What is the technical way to define it? It is in a superposition of two states, which is dead and alive. And before you observe it, it is in that state. But what happens when we observe it? So what happens when we observe it is we have also our own wave equation. Our wave equation is also made up of our own states, the states of the electrons in our body and everything, protons, everything. So when our wave equation interacts with this wave equation, suddenly a wave function collapse happens where the state of this becomes definite, and we either see the cat dead or alive at the same time. So this idea is known as the Copenhagen interpretation of quantum mechanics. So in one sense, we get entangled with this entire system and the state becomes definite. So this is what is known as the reading of observing of a system, where its superposition disappears and we get a finite state as the output. So was this understandable? There are also other interpretations, but again, we are not going there. And you might be thinking, where are we going with all this? We have entered into physics and everything. But no, all of this is actually required in understanding quantum computers. And this is the last concept actually. We'll move on to quantum computers after this. So what is entanglement? Basically, this interaction of two quantum systems in superposition. Then the superposition disappears and one single state appears. Just remember that. So what is quantum computing then? That is exploiting all these quantum properties to perform computations. So I'll just tell you a very basic example, and I think you should get an intuitive feel for why quantum computers are faster. So how do normal classical computers work? So we have some bits and then we have some logic gates. We perform operations on those. Bits, and then we get an output as a bit itself. So this is the truth table. I think everyone has studied about this at least. Yes. So this is what happens in your processor inside your computer, right? Interaction. Yes or no? Am I audible? Right. So how many operations do you think it takes to make this create this entire truth table? How many operations of this computer do we need to perform to get all this truth table? Four, exactly. So on a normal classical computer, it took us 4 separate operations to calculate this thing. Now what happens is we saw that there are some quantum objects in superposition. So here the bits are made up of transistors made of silicon, right? But transistors, okay, made of silicon. What happens in quantum computers is we define bits as quantum objects, like for example an electron, and the electron can then have its we can define its on and off, or 0 or 1 by its spin. If it's spin up, let's say it is 1. If it's spin down, let's say it is 0. So does everyone understand this? And then similarly, so these are two quantum bits, or the name is actually qubits. So we call them qubits. These are different from normal bits. Why? Because they can, obviously, as they are quantum objects, they can exist in a superposition of states. So this is not 0 or 1. This is in a superposition of these states, that is 0 and 1, which is it is a superposition of spin up and spin down. Similarly, this thing. So on normal computers, we use some logic gates. Similarly, there are some quantum logic gates that are there specially. Now, this thing right here, I've written it as quantum AND. Just imagine that this is a circuit. There is actually in actual quantum computers, they don't have an AND gate, but we can simulate by using some other gates. Just like we can simulate every gate using NAND and everything, we can simulate a quantum AND gate. So that just imagine this is a quantum gate. So what a quantum logic gate does, it takes a superposition and outputs a superposition while performing some operations on it. Normal gates take in a bit and then output a bit. This takes in a superposition, outputs a superposition, which is stored in another qubit. So qubits can store superpositions, obviously. So what do you think? This is neither 0, neither 1, and this is also neither 0, neither 1. What will be the state of this? So in quantum mechanics, what happens is that this, we define it as entanglement basically. So this quantum gate entangles these two and performs AND operation on it. So the output that we get is a superposition of all those answers. So all the possibilities, like if this was 0 and this was 0, then the output will be 0 0. Similarly, 0 1 1 0 1 1, and then the AND operation is obviously, this is basically the AND operation has been performed, and then the final output is 0 0 0 and 1. So this superposition 0 0 0 1 of 4 states, there can be a superposition of any number of states, obviously, can be stored on this on this qubit. So in one single operation, we perform the equivalent of 4 operations on a classical computer with 2 bits, and 2 raised to 2 is 4. So with 2 bits, we computed this much. Imagine if we had 100 bits. So we could compute 2 raised to 100 operations in one single step, whereas this would take 2 raised to 100 operations. Can you see how exponentially powerful this is? So we get all the answers at the same time. Now, obviously, one thing that is kind of a black box here is how this gate works. So that hinges on things that depends on what specific qubits. Here, I took electrons as an example. There are various types of quantum computers because there are various types of quantum systems. Like some might use the polarization of light, some might use super cooled ions and everything. So that depends on that, but this works. That is the main point. How do you access or store specific independent states? Yes, that is the catch. So once we have this answer, we have the answer. It is stored in this thing. But the catch is that if we try to read it, like the wave function collapse, like here, it is in both the states. But if we try to read it, observe it, it collapses into one of the states. Similarly, it is in a superposition of 4 states. When we try to observe it, it will get randomly one of these answers as the output, and that is a catch. That is why we don't use this technology already in our smartphones and computers, because it is powerful, but there is this catch that after observing we get one random answer as the output. So we can't use it directly, but smart people have figured out ways to trick this or extract some useful information from the superposition, and that is what we'll look into next. So imagine if we just read this, 75% of the time we'll get 0 and just 25% of the time we'll get 1. So, okay, so there are various quantum algorithms. So I think this is the most famous algorithm, Shor's algorithm. We discussed about RSA and how we use it daily. So it is based on prime factorization, and in prime factor, this person, Peter Shor, he figured out this algorithm which can be run on a quantum computer, and it can easily factorize a large prime number on a quantum computer. how it does that, the process is a bit lengthy and very complex. Not very complex, but very lengthy. See, if you can look into it, there are various steps, and just one specific step in the middle uses a quantum computer, and the information, how this extracts that information is by basically not just directly measuring this, but figuring out the differences in these values. So we can find that there is a machine called a machine that performs a operation called the quantum Fourier transform. Don't get in if you don't know what Fourier transforms are. Also, don't worry. Uh, Basically, just difference between these. Just think of. And there is one more algorithm called Grover's algorithm. Okay, so okay, databases. I think everyone has heard of databases or just simple data, unsorted data. What is the time complexity to find a specific element in an unsorted array? Everyone programs here, I think. Time complexity. It is O of n, if you don't know. So O of n time is used for an unsorted array. But what Grover's algorithm allows us to do is, using a quantum computer, can search through an unsorted array in O of root n time. Okay, so quadratically faster. So this can also help improve things like the brute force attacks. We only have to perform root n operations to crack something. So we can see these algorithms that break cryptography as we know it today, right? O of luck. Okay. So that is why we have this field, entire new field coming up of post-quantum cryptography, which is when quantum computers will get powerful enough to actually break all the encryption algorithms that we currently employ. We have to look for new algorithms which are resistant to quantum attacks. So something we saw the previous diagram, this is exactly the same, just one more thing added to this. As you can see, BQP, this means bounded quantum polynomial. Or so these are the set of algorithms that can be run on a quantum computer in polynomial time. So Shor's algorithm, that by that I mean the prime factorization problem lies somewhere over here. So this can be solved in polynomial time by a quantum computer. So that is not very helpful, right? So we want problems that are even bigger. We want some problem in NP that is outside of BQP. That is what we are looking for. So currently we know quite a few such algorithms. I'll talk about the two most famous ones, and the most famous one is lattice-based encryption. So we all know RSA. We have talked about RSA in, I think, past two episodes. So this is, you as a user of RSA, you won't have to understand all of this. This is exactly the same. So the entire concept of public key cryptography and everything remains exactly the same. You still have your public private key, and you still encrypt data, send it, you still sign things and everything. The only thing that changes is the internal algorithm. Previously that it used semi-prime numbers, and the problem was prime factorization. Now the problem is based on lattices, the maths of lattices. So shall we look at that? So can anyone tell me what this lattice is? So it is just a set of points, and it is defined by two vectors which are known as the basis vectors. So any combination of these two vectors, let's say this is A and this is B. So any combination of these two vectors, the points that they can reach to, this entire structure is known as the lattice. This is a 2D lattice. Can have lattices in multiple dimensions, 3D, 4D, 5D, everything. This idea is clear, right? Lattices. For a plus b is, suppose this is the origin. So a plus b, a and b, or a plus 2b, or a 2a plus b, or 3a plus 2b. You can easily reach any point in this lattice with these basis vectors. Okay, the thing is, in any lattice, there are not just one lattice, one basis vector. There are multiple. In fact, there are infinite. Any pair of vectors you can imagine, like this and this, these two, then these two, as long as they are not collinear, they can be used as the basis vector for this lattice, which means that you can reach any point in this lattice with the help of these two vectors as well, and these two vectors as well. So the idea is then, previously or in RSA, the problem was that we can't factor large numbers. Here the problem is that we can't use any an arbitrary pair of basis vectors to compute the smallest possible pair. So that is the crux of this problem. We can't use this big vector to efficiently calculate this thing. So that algorithm is NP, and that is what we take advantage of. How do we take advantage of it? For example, just think of this, right? If you have to use these two vectors and to reach this point, so you'll have to go somewhere over there, then there, then, because we can also go in reverse, just minus this. But it will take a lot of steps, and finally you'll reach here. So this is a lot harder, and this is very simple, right? You can just go here and go here. So this is our private key, and this is our public key. That is how we use it, and we can't compute it efficiently backwards. So how do we encrypt actual data with it? So this problem is, this approach is known as learning with errors. And what we do is, for all the data that we want to encrypt, there is always a point on the lattice. For example, if we want to encrypt the number 3, so this lattice point can correspond to 3. So how do we send this data to someone encrypted? We'll just pick this lattice point and then add some error to it or some disturbance and pick this point. So this point is still closest to 3, but it is not exactly 3. So now, can you easily reach 3? Can you easily find the lattice point closest to this white vector using these two vectors? Can you do that? What do you think? Is everyone understanding what I'm talking about, all of this? If you have properly attended the last episodes, you should know what RSA and everything is. Therefore, this should be easy. Using these two vectors, it is very easy, right? We can just go here, and check all of these, and then the smallest, the closest point is this. So your encrypted message was 3. That was with the private key. Now with the public key, do you think it is hard? You might think that we can go somewhere like that, but no. If this is because you think that is easy because we are shown the actual lattice. What if I show this now? What do you think? Can you find the closest point here? What is the closest lattice point here? Because you need to find all the points close to it, and then you have to make sure that the point that you select is the closest to it. So this problem is very difficult actually. You have to go somewhere over here, then you'll roam, and finally someday you'll come to some point which is 3. So this is very hard, and this is hard in 2 dimensions. Now imagine, okay, so this was the point that we had to reach. Imagine if we extend this to 1000 dimensions or 2000 dimensions. Your brain can't even imagine it in 4 dimensions. So imagine 1000 or 2000 dimensions. That is the order of magnitude we are talking about here. So this is very hard because it is again NP. this problem grows exponentially with the number of dimensions we add. So in a 1,000-dimensional lattice, this is basically impossible, both for normal computers, that is classical computers, as well as quantum computers. Great. So that was the algorithm learning with errors. And there are various combinations, like in DSA, we had elliptic DSA, Diffie-Hellman, we had ECDH. Here, I think there is a ring-based thing as well. I don't even remember that. So that was about lattice based. That is the most popular approach, and I think the NIST. Have you heard this term, NIST? This is an American, I think, institute which approves and holds a competition for all encryption algorithms and everything. So you see the AES algorithm that we use nowadays. Before it was approved by NIST, it was called the Ryan-Dahl algorithm. Its founder's name, which was Ryan-Dahl. But after it was approved, it won a NIST competition, and then it became the standard. So it was called the Advanced Encryption Standard. That is why we use it everywhere. Similarly, these algorithms are right now the top priority, but they are still not standardized. But we are getting there. The other popular approach is hash-based encryption. So we all have studied hashes in the first episode. Okay. Now the hash-based algorithms can be used for signatures. This algorithm is known as Lampert signatures. Is everyone ready for hashes? Does anyone remember what hashes were? I have a slight feeling that थोड़ा सा ऊपर से जा रहा है सब. I also had a lot of struggle with understanding all of this, but ठीक है. That is a lot of information to take in. One-way mapping, exactly. So in Lampert signatures, so this one is a little bit easier than that to imagine, I think. So in Lampert signatures, what we do is to generate a private key. What we'll do is we'll take this matrix, which is of 2 rows and 256 columns. So 2 into 256, and we generate random numbers in all of them. That is it, random numbers. That is our private key. And how do we derive the public key? We hash it. We hash this entire matrix, and this is our public key. Very simple, isn't it? Okay, so let us look at how we can sign data with this Lampert signatures. So how do signatures work? This was our private key, and this is the hash. So obviously, we always sign for any data, we sign its hash rather than the data itself. And hashes, let's suppose it is a SHA-256 hash of 256 bits size. So you can see there are 2 into 256 bit numbers here in the private key, and there is 256 bit hash. So to calculate the signature, all we do is, if it is 0, we choose the first number. If it is 1, we choose the second number. So as you can see, for it is 0, so we choose 23. If it is 1, we'll choose, sorry, it is 1, we choose 1. If it is 1 again, we choose 9. Here it is 0, so we choose 99. Sorry. If it is 0, we choose the top number, so therefore we choose 72. So this is our entire signature. Very easy, right? Yes or no? So that was how signatures work. And how do we verify these signatures? What use our signatures if we can't even verify them? So let us look at the verification process. It is exactly the opposite. So we have the hashes as the public key. Public key is always available. You know that. and then this is the signature we calculated in the last step, this thing, and this is the hash that is of the data that we want to verify. So there was data, we calculated its hash, and we now to verify, we want to verify its signature. So basically, if for we hash each number in the signature, so we first calculate hash of 23, and then in this thing, in the public key, we'll choose this, will perform the same process. If it is 0, choose the top one, and top one is 23, hash of 23 and 23 match. So the second number is 1, so one hash of 1 and hash of 1 match. Again 1, so hash of 9 and hash of 9 match. So like that, because everything matches, we can verify easily that this message has not been tampered with. That is the entire algorithm. Can anyone tell me the flaws of all of this? Why should we not use it? This was developed way before even, I think, RSA, hash-based signatures. This is considered to be quantum resistant. But one major flaw in here is that they are one use only. So every time we have to generate a public-private key pair, and they can be used to sign only one message. So why is that? Because every time we create a signature, we basically give away half of our numbers in our private key. So you can imagine, as we keep encoding and signing some data, eventually someone will be able to figure out every single number in our private key, and then it will obviously be vulnerable to attacks. So this is used only once. But then what is its benefit? Like the things that we use today, RSA and everything, they are permanent, right? We can assign unlimited amount of messages with them, and this is just one use. So we can't directly use them with servers and certificates and everything. It would be useless. So the idea is to mix them with something known as the Merkle trees. So does anyone have any idea or heard about these trees? I think we use them in blockchain as well. So Merkle trees, what they are is, the tree is constructed by basically hashing child nodes. The value of a parent is basically the hash of its child nodes. That is its value. So value, this has some value, and then the value of the parent node is hash of this and hash of this, and the hash of the all of it. Did you understand this? So let's say this was A and this was B, then the value of this will be hash of A plus B, and the A and B itself are hashes. So all of them are hashes, and every node up to the root node is consisted of hashes. All right. So what we do is we generate this Merkle tree, and how do we generate it? We know that we can generate a private key here. So what we do is we generate n number of private keys. Let's say we generate 100 private keys, and then we'll construct a binary tree and construct this whole Merkle tree from it, calculating hashes recursively until we reach the root node of this binary tree. What happens now is this root node, the hash of the root node is your public key, and each of the leaves that we use to create this tree are the private keys, and each private key is used once only. So once you use it, you have to basically never use it again. So if we create a tree with 100 nodes, every time you have to sign some message, what you'll do is you take a leaf node and then use it for Lampert signatures, and just instead of just giving away directly next hash, the next direct hash of that thing in the public key, like we did here, what we do is we give them the entire tree, entire path to the root node of the tree. So this is all the hashes till the root node, and everyone can verify this. So it is the same idea. You can think about it a little, you'll get it. So that basically just makes it so that these signatures are not used once only. You can use them 100 times before this is exhausted. If you create a big tree of thousands and thousands of signatures, you can use them multiple times. That is the entire idea. Okay, was that clear? Hmm. That is the last topic of discussion today, actually. And this is also obviously used in blockchains because you can just imagine all the transactions on the blockchain are leaf nodes and then hashes of those, because we have to calculate one single hash for each block of the blockchain. So we can have that by constructing this tree. That it is also used there, and you can also use it here. This is also proven to be quantum resistant. Great, then. I think that is all for our discussion today. Which of these topics did you find very interesting, and which ones did you not understand at all? This was the last episode of this season, the season 4 of FOSS Files, and we discussed so much about cryptography, and yet there is so much to explore. As we saw about all of these things, there are lot many other things in cryptography, and I hope you'll take this opportunity and inspiration to actually go ahead and explore all of these things, especially the things that I mentioned, like Shaw's algorithm and everything. Very well presented. Okay. Uh, does anyone have anything else to say? Does anyone have any thoughts or any ideas about these things? Season 5 was amazing. Did I say season 4? I think I said season 4. Really sorry for that. This was season 5. Learn a lot. Great. What do you think we should cover in season 6? Physics and computing. So physics, blockchain depth. Yes, we can do that. Let's go hardware. Like actual silicon transistor level hardware, physics, also quantum computing. This was, I think, our longest episode. We started at 10 p.m. and it is 10:50 now. Signing off.